All right, so last time we saw that if we have an alkene and if we add some mercury acetate, some water, and then after that add some sodium borohydride, we end up with Markovnikov addition of the alcohol. And so naturally you might be thinking, well, what if I wanted to take an alkene, react it with something, and get anti-Markovnikov addition? Could we do this? And if so, what reagent would we use? And so naturally the answer is yes, we can do this. The reagent we would use here is borane, which is BH3, and usually in a solution of THF. THF stands for tetrahydrofuran. It's essentially this like kind of cyclopentane, except now that one of the carbons is an oxygen, but you can use other ether solvents. Maybe diethyl ether is another popular one. And then in the second step, we're going to do is add some hydrogen peroxide and some sodium hydroxide. So let's go ahead and take a look at this mechanism. And the first thing we're going to take a look at is the borane. So the BH3 again stands for borane. And so if you think about borane, it's a planar molecule, right? Trigonal planar. And it doesn't have 8 valence electrons, right? It has this empty p orbital. And so what that means is that it can accept electrons into this empty p orbital, and it acts like a Lewis acid. And Lewis acid is an electron pair acceptor, which makes this borane overall very electrophilic. So it wants electrons to come in and attack. And so in this first step of this mechanism, what we have is the attack on the borane by the pi bond. And so we're going to do this asymmetrical alkene, and we're going to take a look at this BH2, right? We're going to attack here, attack our borane with our double bond, our boron, and then this BH bond is going to attack here. And so you can think about there's one of 2 possible outcomes for our intermediate or our transition state. Right, we can have the bonds form like this so that the boron goes on the less substituted carbon. Or we can have the reverse, where the boron goes on the more substituted carbon. And so there's a variety of factors we can think about. One would be sterics, right? If we think about here, we've got the big thing over here and the big thing over here. So we've got big things away from each other. So this is good from a sterics perspective. Whereas on this side, we've got this kind of bigger thing over here along with this bigger thing over here. That's bad from a sterics perspective. So the sterics favor the left side. So let's go ahead and move sterics kind of over here. And then the other thing we can think about is the kind of electronic effects. And so one of the funky things about boron, it's actually less electronegative than hydrogen. So hydrogen is actually more electronegative than boron, right? So this hydrogen is actually partially negative, and this boron is actually partially positive. And then we'll just mark that on this side as well. And then we can think about our alkene. Right, so this is the alkene that we've got, and so we can draw some resonance structures. One thing we could do is move both of our double bonds to the more substituted carbon. Or we could do the reverse, right? Move these electrons to the less substituted carbon. And so if you take a look at these 2 resonance structures, one of them is actually better than the other, and it's this bottom one is better, right? This bottom one has this tertiary carbocation, and that's much better than this primary carbocation. And so when you're looking at this alkene, because of this better resonance structure, this carbon over here is actually partially positive, And then this carbon over here is partially negative, right? And so if we kind of put those partially positive and partially negative charges over here, and then we remember that opposites attract, right? We've got opposites attracting here, and so that's good from an electronics perspective. And then here we have the same things kind of right next to each other. If we think about two positive charge is next to each other, that's bad overall. And so this right side essentially does not form. And so what happens is we get the borane attached to our less substituted position. Right, and so there's kind of an intermediate or a transition state, depends how you look at it. But basically what's going to happen is we have this double bond here. It's going to attack this boron, and then this bond right here is going to attack over here. And so what we end up is adding the hydrogen on the more substituted position and the BH2 on the less substituted position. And this is where our regio selectivity comes from.